So it's, yeah, it's maybe some false advertising in the abstract. Hope that's not too offensive to anyone. But so thank you, Yannis. So I wanted to talk about some things that appeared in my member seminar talk, but I'm not going to assume anyone was there. I'm going to give a different perspective on what ends up being the same problem. So, but now I want to have a more of a representation theoretic point of view. So, so what is the goal? So, you know, if we're studying, if G is a group, one of the central objects that we're interested in studying is interested in the vector space of some kind of maybe some kind of generalized functions, class functions. Class functions, so let me just think of some kind of, let me call it some kind of functions in quotation marks on G mod G. So I'll use G mod G to denote quotient of G by conjugation. So this is kind of one of the main things we're interested in representation theory. What class of functions depends on what kind of representations we're looking at. I'll be more precise later. So what do we know about this collection? There's two main things about class functions is that this is the home to characters of representations. So this is where characters of representations naturally live. They give you class functions on the group. And the other kind of dual role is that this vector space is the center of the group algebra in nice situations. Say, let's assume, say, G is a finite group. Just to be concrete, then and I just mean, say, complex valued functions. This is the center of the group algebra. In particular, what this tells you that this is, in particular, saying that this is a commutative ring under convolution. So we look at class functions on the group. They sit inside of all functions on the group. We can perform the convolution product. And if you look at class functions, they end up being a commutative ring inside of there. In fact, the center of the group algebra. And you know, what do we want to do in representation theory? We want to kind of Fourier transform or Poincaré theorem. We'd like to kind of a version of the Fourier transform. I'd like to maybe describe this commutative ring in some concrete way. I'd like to describe this class functions under convolution. I want to identify them as functions of on some spectrum, some space, some dual, some space of representations with pointwise multiplication. So that's kind of I'd like to describe the set of, if you'd like G, if you're a finite group, I'm thinking about the set of irreducible representations. Functions on the set of irreducible representations with pointwise product are identified with class functions with convolution. So this is kind of one of our basic goals in representation theory. What I'd like to talk about today is a kind of a geometric analog. And the word geometric is being used in the sense of, say, the geometric Langlands program, or geometric representation theory more generally. So in geometric representation theory, and I'm going to be in a very specific context here. I'm going to study G. A group is going to be a reductive group over the complex numbers. That's the particular geometric representation theory I'm setting up, living in. So we have, you know, so maybe just imagine we're talking about SLNC or something like that. Then what is there's going to be an analog. The analog of the space of class functions is the category, which I'll call D of G mod G. What is this category? This is, let me maybe use different notations that I'll get used to. So here, let me give notation. So what is this? D sub G, for any space X, I'll use D sub X to denote the ring or the sheaf of rings of differential operators, polynomial differential operators on X. So D sub G means G is affine. I just mean the ring of differential operators on the group G. So we look at the modules for the ring of differential operators in the group G, and we want to look at the ones that are equivariant under conjugation. Okay? So maybe we can, I don't know if we can discuss exactly what the equivariance means in a second, but maybe does everyone have some picture of what this kind of thing is? Look at a system of differential equations that's invariant under conjugation. Okay. We'll give examples in a second. So this is going to be the central object we're interested in. We're looking at differential. So there's another way of saying a module for D. This means a system of differential equations. These are the collection of all systems of differential equations on the group that are conjugation invariant. So this is what I want to call like a class D module. Okay. Now, why are we interested in this? There are many motivations historically. Maybe the most important one, or the oldest one, is if I did the elatic version of this. So I have maybe some group defined over a finite field, and I look at some kind of elatic sheaves on the group, some category of elatic sheaves on this. If this was, and then I look at equivariant, that are equivariant for conjugation. So this is the kind of elatic analog of this space. This is the home of Lustig's theory of character sheaves. So Lustig, in the elatic setting, we have a precise map. We have a precise relation between sheaves on G over the algebraic closure and and functions on the group itself. We apply the function sheaf dictionary of Grothendieck to land in honest class functions on the finite group G of f cubes. So such a sheaf is a machine that produces class functions on G of f cube of any of its extensions. So in the elatic setting, there's a direct map between this sheaf category and the vector spaces of functions you're interested in representation theory of a finite group. And this is the home of where Lustig developed. Lustig developed a beautiful theory of characters of representations of finite groups that actually have geometric avatars. They're actually sheaves here that produce the characters of finite groups of Lie type. Yeah, so so here I need to in order to apply the trace of Frobenius, I need a sheaf that has the Frobenius equivariant. Then I take the trace of the Frobenius map to some power. I get a function on the set of points here. And if it's equivariant sheaf, I'll get a class function. OK. I'm not saying anything precise. This is not the setting I'll be dealing in. But this is the motivation for a lot of geometric representation theory comes from this elatic situation where you have a direct map from the categorical version to the classical version. A more direct historical motivation is Harishandra's work. So Harishandra was interested in, he wanted to study the distributional characters. So he studied the characters of admissible representations of real forms, of real reductive groups. And the way he studied these characters, which are a priori give distributions on the group, he studied them using a system of differential equations that they satisfied. So he said that if I have say irreducible admissible representation, let's say if I have an irreducible, say for example, a unitary representation, then the characters are solutions to a G invariant system of differential equations on the group. There's actually something defined on the complex group, the Harishandra system. So you study these characters by describing them as solutions to a system of differential equations. This is a very, very nice system. It's a holonomic system. And the holonomicity means that the system of differential equations determines the function up to some finite dimensional ambiguity. In fact, and in Harishandra used the amazing properties of this particular system to prove all the regularity theory and prove all that these are actually not just distributions, are actually functions and with very nice properties. But the key tool is this theory of these invariant differential equations. What is this invariant? It's not something very mysterious. So let me give you an example element in D of G mod G. This is the most interesting guys in some sense, or the most basic guys in D of G mod G. Let's call them M lambda. These are going to be the Harishchandra system. Chandra system. So what is, so how do I define this? First, I think of the enveloping algebra of G. The enveloping algebra of G can be thought of as differential operators on the group that are invariant under, I don't know, say left invariant differential operators. And inside of here, I have the center of the enveloping algebra. And the center of an enveloping algebra I can identify with differential operators on the group that are invariant both under left and under right. Okay. So inside of this ring that I'm studying, this ring of differential operators, there's a commutative subring, the ones that are invariant under both left and right action. And that's the center of the enveloping algebra. OK, so I have a commutative subring inside of this ring of this non-commutative ring of differential operators. So I can look for eigenvalues. So I can look at the Harishchandra system. So here I'm going to look at, well, I need to, this center has a description. Also, the Harishchandra isomorphism tells you that this ring is isomorphic to a polynomial ring in rank many variables. It's a polynomial ring, but concretely, it's a polynomial ring on a space. Let me call C, where C is the spectrum. Well, tautologically, it's the spectrum of the center. There are functions on their spectrum. But it's the, well, OK, sorry. So C, let me just say what C is. It's given by the Cartan subalgebra modulo the action of the Weil group. Okay. So this is the, if you'd like, this is also the geometric quotient of the Lie algebra by conjugation. Okay. So I'm going to use this double slash here. This double slash here is to indicate I'm taking the vector space, the dual Cartan subalgebra, and I'm modding out by the action of the Weil group. But I'm not modding it out in a kind of a stacky or orbifoldy sense. I'm just taking the usual affine quotient. So look, spec of invariant functions. And so this is really isomorphic to just an affine space. And this is the way Yannis used the same notation today, right? The GIT quotient, just spec of invariant functions. OK, so now my parameter for the Harishchandra system is going to be a point in here. So there's a point in the spectrum of this ring of, again, this is, again, just to reformulate what's there, this spec of this ring. So given us a point in the spectrum, I can write the Harishchandra system, which is I look at the ring of differential operators on G, and I mod out by the ideal generated by Z minus lambda of Z. I write it kind of informally, where Z is in the center. So given an element of the center, lambda gives you an eigenvalue for any element of this ring. So it gives a homomorphism, right? So lambda is a homomorphism from Z to C, is evaluating at this point. And I just impose that eigenvalue. Okay. So I'm writing it as a system of differential equations on the group. But because of this invariance property, you can check that this system is invariant under conjugation. Okay, so I'm not going to write it directly on G mod G. G mod G is somehow not an affine type object. I don't want to write things on G mod G by modules over rings of functions. It's easier to just write up differential equations on G. And then this system is going to be invariant under conjugation. So this is an example of one of my, this is the most interesting example. Or most basic example. OK, yeah.
For holonomicity, you also need to impose some k-finiteness.
I don't. Yeah, so that's a good question. So one of the miracles here is, right, on the group itself, this is not a whole lot of equations. This is rank many equations. So it's very far from holonomic on the group. But on the adjoint quotient, on G mod G, this system is holonomic. So what you're referring to, Harishchandra used the same technique to study matrix elements, k-finite matrix elements. And if you look at, say, G mod k, on here, the system is also holonomic. The same system in proposing these. But it's, maybe you'll tell me this is the group version. But in any case, this system is holonomic on G mod G or on G mod k. Okay. All right, so and that's where the Harishchandra system. So in other words, we're solutions. We're studying joint eigenfunctions. So we're studying the collection. Maybe let's just write it in another way. We're studying functions. A solution of this D module is a function that delta I equals lambda I f, where delta I are, say, the generators. These are the generators of the center corresponding to kind of the Casimirs. There's rank many of these guys. I equals 1 to rank. And we're just looking at joint eigenfunctions for these Casimir operators. OK. And the point of Harishchandra is if I give a character of an irreducible representation, on an irreducible representation by Schur's lemma, the center acts by some scalar. And you translate on the level of characters, that tells you that the distributional character of that representation will satisfy this system of equations. And that ends up telling you a huge amount about the character, just studying these system of equations. OK, so let me give the let's step backwards. A classical analog of this is the usual Fourier transform. So we'll maybe leave the setting of reductive groups for a second. Let's suppose that group G is just the complex numbers. And then the analog of the center of the enveloping algebra is just polynomials in the differential equation, in the differential operator ddz. So these act as differential equations. And then we're looking at the system of differential equations where now lambda is a complex number. And the system of differential equations is the differential equation f prime equals lambda f. That's what we're looking at. And our solutions are f equals e to the, so the solution of this equation is f equals e to the lambda z up to a constant. So this system, this system of differential equations determines the exponential function uniquely up to a single constant. So this is, in some sense, the fundamental thing that happens in geometric representation theory. We don't have the function sheaf dictionary. We don't have Frobenius. But when you see an expression like e to the lambda z, which is not an algebraic function, we notice, well, it satisfies an algebraic differential equation. And that algebraic differential equation determines this function uniquely up to a scalar, or for more complicated special functions, up to some finite dimensional ambiguity. So we're going to kind of use this dictionary. It's a kind of complex analog of the function sheaf dictionary. We're going to think of systems of differential equations as avatars of functions, which are given by their solutions. Okay. So algebraically, I don't know how to think of the exponential function directly. I think of the system of differential equations it satisfies. And now I can do Fourier theory with the systems of differential equations instead of with the functions. So these m lambdas, these are the analogs of character sheaves. So you can define precisely what a character of a geometric character of the group, of the additive group is. And these are exactly the character sheaves, just like the exponential functions are exactly the characters of the additive group. OK. Now here, back on C, we have the classical Fourier transform. So the Fourier transform says that I can think of writing distributions instead of as functions of z, I can write them as functions of lambda. I can think of distributions, say tempered distributions, a dual Schwartz space. I can think of, instead of writing them in the parameter z, I can think of them as writing them in momentum space, writing them as functions of lambda. So so Fourier transform says well, we can study systems of differential equations on C locally in momentum space. So in other words, given an open subset of momentum space, it makes sense to think about systems of differential equations that live over that open subset in momentum space. Let me try to say a precise statement here. What do I mean by this? There's something, it becomes kind of a very silly. If you look at the ring of differential operators on, let me instead of C, let me have a vector space, just so I distinguish C from its dual, right? So the ring of differential operators on the vector space and the ring of differential operators on the dual vector space are identified as rings. So if you like, I have polynomials in functions that are generated by z and ddz. I identify with functions in t and ddt, where I just up to a sign just replaces. So this is what the usual Fourier transform does. It switches z and ddz up to a sign. So you have an isomorphism just of rings. This is just an isomorphism of rings. So you have an isomorphism for the category of modules. You have an equivalence of categories between the categories of modules on V and on the dual vector space. And if you like, this is a kind of the fact that the Fourier transform exchanges convolution multiplication can also be said here. There's a convolution operation on this side, and there's a tensor product operation on this side, which will get exchanged. So this is a version of the Fourier transform. But all I really want to to get out of this right now is that the systems of differential equations on V I can think of microlocally. I can think of them as depending on the momentum space, and I can restrict them to open subsets in momentum space, or I can impose equations on them over momentum space. OK. Did that make sense, this analogy? Okay. What I'd like to do is do this picture for G mod G. Okay. So that's our goal, is to develop some kind of Fourier transform instead of for characters of the complex of the additive group, which we understand, for characters of complex reductive groups. So we replace C by G mod G. OK. All right. So the goal again is I'd like a Fourier transform, or let me say it more. I'd like a spectral decomposition or momentum space picture decomposition for the systems of differential equations where the Harishchandra system lives. And maybe my first guess of what the parameter space, the momentum space picture should be, it should be over this space C, which is spec of the center. So I'd like to, this is not going to work, but that's my first idea. I'm going to try to understand systems of differential equations as living over this parameter space, this space C. Why, again, might you think that? Well, it works classically. So if you take the classical limit of this is the kind of thing we've been. OK, I have a lot of things I want to say, but I'm also noticed I'm talking very fast. So you should stop me, and it's OK? All right. Too much caffeine. So what's the classical limit of what we're trying to do? We can look at, you can replace what's on that board with something classically. You can look at functions on the cotangent bundle of G. You can look at symbols. This is where symbols of differential operators are. And you look at symbols that are left and right invariant. That's analog of differential operators that are left and right invariant. And well, these you can use one of them to identify this with a product. And so this just becomes functions on the dual of the Lie algebra that are invariant under conjugation, which is the same ring that we had before. So spec of this ring is the same space C. The same class parameter space appears classically.
Just to
Yeah.
clarify,
Yeah.
D of G mod G is not modules for ZG.
D of G mod G is a very complicated. Yeah, that's right. It's a no-sense modules for DG. Sorry, I'm trying to get this guy, right? I'm just saying. Yeah, so I'm saying that D of G mod G, let's do our SAT, right, is to ZG as T star of G mod G is to, I don't know, to the same ring. But I guess functions on G invariant polynomials. Okay. This space.
What is this space?
OK, what is this space? Good question. Well, OK, so what is the space? It's the first. Well, let me just remind you that if I have a space F, if I have a G space X, and I want to understand the cotangent bundle of X mod G, this is not given by the cotangent bundle of X mod G, but it sits inside of there as the fiber over 0 of a moment map. So to get a cotangent bundle of a quotient, you have to do it's a subquotient of the cotangent bundle of the space. You have to quotient out by the group, and you also have to kill the action of the Lie algebra. So that's so it's a fiber. It's a fiber of this map. So that's Hamiltonian reduction. So what is T star of G mod G? Well, it's not just the cotangent bundle of G divided by conjugation. I also have to impose this moment map. Let me just give you the answer. it's a collection of pairs of an x in the Lie algebra dual and a g in the group such that g is in the centralizer of x up to conjugation. So that's a calculation. It's what's called the inertia. It's the inertia stack of G dual mod G. So it's an element of the Lie algebra and a group element that's in its centralizer up to simultaneous conjugation. OK. So that's the thing of which we're quantizing, if you like. But it's easier to not think stackily, just forget about these things, and just think of we're just looking at commuting pairs in the group, element of group and element in Lie algebra that commute up to simultaneous conjugation. OK. Why am I mentioning all this? That well, this quotient of G star by G doesn't have, it's just this. I mean, this is G star mod G. It's an element of G star. It's a pair.
When you say mod, what do you mean?
A stack quotient.
Okay.
Yeah, my quotients will all be stacks unless I put a double line. But yeah, so it's just commuting pairs. I mean, if I think of this as the Lie algebra rather than Lie algebra dual, it's just commuting pairs of elements in the group and the Lie algebra. And then I mod out by conjugation. So the moment map condition is just that they commute.
The moment map commutator?
Yeah, yeah. It's gx, g inverse minus x. Yeah, exactly. OK, so if I study, maybe I should say it a little less technically. If I study T star of G, or T star of G mod K, or T star of G mod G, anything I start quotienting out by, all of these spaces all have a map to C, looking for map of action of the invariant polynomial. So I have this map from the cotangent bundle of G to C, which is just look at the values of all of my invariant functions, right? So C is functions on T star G that are invariant both on the left and on the right. So they're invariant under anything you can think of. And so take any of the spaces you can think of that are made out of G. They all come with maps to C, right? Just the values of these invariant polynomials. And so that means that it means that it makes sense to take a fiber of these maps. So the fiber of these maps is going to be, so given a lambda in C, I can look at the fiber over lambda in any of these spaces made out of G. And so you can think of, if you'd like, all these spaces kind of spectrally decompose over C. So my maybe let me try to write a statement. So these so what is this? OK, let me write it over here. So what is the picture here? The picture is that these Harishchandra modules, if you just compare the analogy, the classical and quantum analogy, this m lambda is the quantum analog log of the structure sheaf of the fiber over lambda in T star G mod G. So here I have a commutative ordinary space, T star G mod G, has a map to the space C. I can look at its fibers. So if I'm studying sheaves on T star G mod G, a very basic thing you could do is take a sheaf that lives, that's just a structure sheaf of a fiber. Okay? So that's what the Harishchandra systems are. They're just the analog of that. I'm just imposing these equations. But what I'd like to do is not just have the structure sheaf of a fiber. I'd like to have an analog. So here's a question you can ask. What is analog? What is the quantum analog of all sheaves on the fiber over lambda? I'd like to have an actual spectral decomposition. I'd like to take, say, all coherent sheaves on this space. Well, and there I can study them fiber by fiber. In the quantum version, I understand what the analog of a structure sheaf of a fiber is. But I don't, as of yet, know how to really spectrally decompose. I don't know how to say what is the collection of all sheaves that live on a single fiber, or how to take the whole category and break it up according to lambda. I don't yet have a Fourier transform. I have the analog of exponentials in some sense, but I don't have the Fourier transform. Okay. I'll try to make that more precise, but that's what we're trying to get at. Okay. We're trying to do this is the question we want to answer. All right. And the point is there won't be such a thing. This doesn't exist. Our space differential equations on G mod G don't actually live over C. I'll explain that in a second. Let me give one more familiar analog for what we're trying to do, which is kind of the infinitesimal version. Instead of the group, let's just look at the Lie algebra. So the infinitesimal version of this picture is, suppose I'm studying just modules for UG. Or if you'd like, there's a similar picture for GK for Harishchandra modules, so representations of admissible real groups. But let me just forget about K for a second. Suppose you're interested in studying representations of G. How do you understand? So this is an analog of the Bernstein center of in the p-adic setting. If I study one of these categories of representations, there's a natural space over which they live, the analog of these Bernstein components. Well, we have, again, Z is the center of UG. And so given any UG module, it becomes a module for the center. And you can ask, how does the center act? So that means that the whole category of UG modules, it decomposes over C, which is spec Z. So, this space, C, provides a space of continuous parameters in representations of G. So when you study representation of a Lie algebra, the first thing you do is you have the continuous parameter, which is the action of the center. And then, depending on the exact setting you're looking at, you imagine that for you fix lambda, the collection, you have some kind of finite or small collection of representations with that fixed infinitesimal character. So the continuous parameters in representation theory all come from C. But there's kind of these packets of representations for fixed lambda. Okay. But we have a natural base. So given this decomposition of C doesn't give you the full plancher, doesn't give you the entire description of representations, but it's kind of the continuous part. OK. It's kind of the natural geometric base. So we'd like a similar picture instead of UG modules for our D modules on G mod G. OK, so let me try to. So what is the? But in fact, as we said in the beginning, class functions are not just a vector space classically. They're a commutative ring. So what I'd like to do is ideally would like something like a Fourier transform. So our spectral decomposition should be something like this. I take this collection of differential equations with its operation of convolution and identify them with something like vector bundles or coherent sheaves or something like that on some space, let me call it C, with tensor product. This would be the dream of a Fourier of kind of a Fourier transform. You want to say that there's some space of geometric space of parameters over which everything lives. OK, so let me try to explain this dream. So first of all, I have to tell you what this convolution is, right? So that's important structure I have on class functions is that I can convolve them. What is the analog of convolution here? So if I look at the collection of just let's forget about equivariance. You just look at the modules for differential equation for the systems of differential equations on G. This guy is a tensor category. It's a monoidal category. It has an operation of convolution. So to understand this, I think it's useful to just think of G as being finite group. Right? That's how I always just think of G as being finite group. And here we're just looking at vector bundles on a finite group. If I look at vector bundles on a finite group, I can see all the main structures I'm going to talk about. So if I have two vector bundles on my finite group, and I have a vector bundle V, I have a vector bundle W, I could take their external product, which is a vector bundle on G cross G, and I can push it forward and define a vector bundle on G, which is the definition of convolution. It's just the analog of convolution in the group algebra. So here there's an analog of this for differential equations. The push forward, what does it mean push forward? It just means if I have a function here, it's satisfying some system of differential equations. The push forward system, let me write this. If I have so under the Sheaf dictionary correspondence tells you what push forward is. If I have a function and it satisfies some system of differential equations, then I can imagine integrating it over the fibers of a map like F, and that's what the push forward should do. So if this is a solution of this system of equation, the integral should be a solution of the push forward system of equations. And that kind of determines what push forward is.
The Fourier transform always has some unitarity somewhere in order to actually compute it.
Right.
Make sure you have all the representation. Is that ever going to come?
Not today.
It will.
Not for me.
It's not part of this picture. What I'm saying is, you talk about a Fourier transform, and it just seems to be at the formal level just of the algebra. How are you ever going to prove the Factorel formula?
There's categorical analogs of the structure.
At what point, so in Harishandra's work, at the end there's kind of the template spectrum,
right,
which contributes to the L2 of G.
Mm-hmm.
And that's kind of where you kind of know you have all the guts.
Right.
Before that, you don't.
Right.
Otherwise, you're just writing down and you're just sort of formally manipulating. So
well, first of all, there's a story for the classification, Langland's classification for admissible representation. So
that Harishandra doesn't.
Right.
His big thing was to understand L2 of G as a
right. So you can understand that in the demodule setting as well, but I've not.
So there is a structure, and you get that.
Yes. Yeah. Well, let me not say Hilbert space. There's invariant non-degenerate forms. Let me not say. It's hard to say. That's not really. Tempered ones you don't understand. You don't understand the unitary dual. You understand the tempered dual in this language. Yeah. So but yeah, the unitary dual is a mess. Okay. So yeah.
So
yeah.
DG includes the center, so your modules will be modules for the center.
Yes.
Can you explain somewhere in the convolution where we lose the ability to consider them as sheaves over spec of the center?
No, you can. Let me get to that. Maybe the main point. I'll say it in more detail. The point is that the center is not in the center, right? The center of UG is not central in the ring of differential operators. That's the basic problem. There is no center to the ring of differential operators. So you might think they're central in UG, but that's not really what doesn't help you. I don't want to get too much into the technicalities. Let me just say, so there's this analog. This is kind of an analog of the group algebra. So there's a convolution operation. There's a multiplication on these D modules, and then you ask what is its. So then you can calculate what's known as the Drinfeld center. So the analog of the center in this setting. And again, I could take G to be a finite group if you want. I ask, what does it mean to be central? So these are things that commute with everything else under convolution. And if you just ask what it means to commute with, say, a delta function, you ask just the fact that you commute with a delta function will tell you, for every element in the group, will tell you that M has to be invariant under conjugation. So if M is in the center of the group algebra, then it follows that it has to be invariant under conjugation. It's harder to prove, but in fact this is exactly the center. So that requires more tools of kind of categorical harmonic analysis, but this ends up being exactly the center. Right. So the Drinfeld center. Okay. There's two answers to your question. If I give you a monoidal category, So let's imagine C is, say, an abelian category with a or say a k-linear category with a tensor product, exact tensor product. Then the Drinfeld center it's the category of pairs where I have an object M in C, and I have a centrality. So now being a center is a structure. I have a structure which identifies left multiplication by M with right multiplication by M. So a functorial isomorphism, a natural transformation, natural isomorphism between left multiplication by M and right multiplication by M. So in particular, that's where I got this equality. I was testing it against skyscrapers. That tells you that these things have to be equivariant. Now, oh, thank you very much. Yes. Yes, the center of the group algebra is class functions. That's the analogous statement. Now, but I want to point out something subtle that happens here that that makes sense for G to be. Take G to be a finite group. In fact, take G to be any group. I don't know. Just think of Z mod 2. For any group you can think of, this category, this Drinfeld center, the center of vector bundles on G, well, these are going to be identified with vector bundles on G mod G. And this has a natural convolution operation coming from convolution here. The thing that's surprising when you first see this is that for any group whatsoever, this category is not actually commutative. The center is not commutative. Or more precisely, it's not symmetric monoidal. If you look at the definition, you'll always see that for any two objects, I will certainly have an isomorphism between V convolved with W and W convolved with V. That's part of being in the center. But being symmetric monoidal is stronger. The commutativity on this level is now you can ask the question, what if I do this isomorphism twice? I have an isomorphism from V tensor W to W tensor V. I can do it twice. And you can ask, is this identity or not? And the answer is never yes. Even though think about, I think, just thinking through the example of a finite abelian group is already, even Z mod 2 is enlightening. That this category, it's always a braided tensor category. This guy is an example of a braided tensor category. It has an isomorphism like this, but it satisfies a more complicated thing. It satisfies the braid relations. OK. I don't know if it's a good exercise to do. I can give you some hints, like maybe, what is vector bundles on G mod G? There are two obvious pieces on there. For G commutative, there's just vector bundles on G themselves, and then there's representations of G. Right, so G mod G, if G is commutative, G mod G looks like G cross point mod G. And so inside of here, you have vector bundles here are representations of G. Here you have elements of G. And just compare when you try to move across a representation by an element of the group. When you do this transformation twice, you'll get something related to the action of that element on that representation. That's where there's something non-trivial. This map is not identity. It has to do with the action of a group element on the corresponding representation. So this is just to say that in categorical representation theory, centers are not commutative. That's true also in ring theory. If you take the derived version of a center, derived version of center, that's Hochschild cohomology, is not commutative. It's analog of braided. So centers are not commutative. So this kind of dream of a Fourier transform has to be refined. I can't hope to describe G mod G as sheaves on some space with a tensor product, because that's always commutative.
So that is also D of G, right?
Yes, sorry, thank you. That's D of G. OK. OK. So all right, so that's yeah. So I'm saying that if I have an element of this group algebra, this category of sheaves on the group, that's in the center.
Which is a bit of extra data.
Which is a bit of extra data. It's giving this isomorphism for every object of a way of moving them around each other. So I applied this just to skyscrapers in particular. And you ask, what does it mean to convolve with the skyscraper? That's just a translation. So I get an isomorphism between my sheaf, and it translates for every G under conjugation. So it's left. So I have left translation and right translation by the group element. If I look at this system of isomorphism, I'll get an isomorphism between M and delta G inverse. I'll get an equivariance under conjugation. I'll show that the module M and its translates by conjugation are identified. That comes out of, that's what this system of equation is telling me.
So you're saying, what you're saying was a function from the center to D of G mod G.
That's right.
Which commutes with projection above to D of G.
That's right. And the claim is it's an equivalence.
Oh, it's an equivalence.
It's in fact an equivalence. Yeah, that's not automatic. That uses, I have a proof of that, the theorem of Gates-Gorey, and that somehow ends up not being as easy as you'd like. I guess maybe one thing I'm hiding under the rug is everything I'm doing here is actually derived, and so I'm trying to suppress the derived version of things. But these categories, like categories of D modules and G, don't behave very well as abelian categories. These functors of convolution, these push-forward functors, are not exact. And to get a well-behaved algebra, really, I need to think of all of these as, that's why I keep saying let's do finite groups, because then we can ignore the derived stuff. So when I'm saying this Drinfeld center here, I'm really meaning a derived version, which is derived version of Drinfeld center. Or version of Hochschild cohomology. OK. So this is just to say that when you're trying to describe G mod G, you want to describe G mod G with convolution. That's the center of the group algebra. But you're never going to have something like this. But you might hope at least to find a big commutative piece inside of there. So what do we mean by a spectral decomposition? So let me just say kind of some more formal things, and I'll go back to an example that'll make things much more concrete. So if I have a tensor category, what does it mean to say that it lives over some space, or to give a spectral decomposition? Spectral decomposition over some commutative ring, one way to say it is that you want to give a functor from modules for this ring with tensor product to the center of this category with its convolution. What concretely this means, what does this mean concretely? It means that I can take any vector bundle on this. So let's call spec R, that's going to be my base. I could take any V, a vector bundle on the base, and I can tensor C so I can tensor elements in C by vector bundles on the base. So this is a version of the spectral decomposition. Classical spectral decomposition, I would take a function on the dual. And functions on the dual, I act in the group algebra. Act in the center of the group algebra. Here I have vector bundles in the dual. I can tensor them in the group algebra. OK. So in particular, so this is, or you could say this abstractly, this is, maybe this is going off the deep end here. Another way to say it is that C forms a sheaf of tensor monoidal, a sheaf of categories over spec R. So you'd like to understand, what does it mean? A spectral decomposition means to take your category and sheafify it over some base. And that's in particular will make sense of what we're trying to do, this idea of working microlocally to restrict an open subset in this momentum space. Yeah.
You're saying just giving a functor from R mod and tensor product to the center of C is the same as saying C is in some sense a sheaf of categories.
Yeah. Yeah. So I mean, if we ignore the tensor structure, if we just think of what it means to have So if I give you just a k-linear category, let's forget about the monoidal structure. You can ask the same thing. So suppose I give you C is k-linear. You could say it in the abelian world too. So just say k-linear abelian category. And so I can ask. So the claim is there's several structures I can give on C that are equivalent. I can upgrade C to an R linear category where R is some K algebra. So say R is commutative K algebra. So you can ask, what does it mean to be linear over a base? And so I could say I can upgrade C to an R linear category, or I could say map from R to the Bernstein center, to the endomorphisms of the identity function of C, which is kind of the Bernstein center of C. Or I could say C is an R mod module category. So I could take C and tensor objects of C by modules for R.
Let's have the Fourier transform.
Hmm?
Let's have the ordinary Fourier transform.
Yeah.
What is your spectral decomposition?
So if I'm a spectral decomposition, I take here I'm just take a system of differential equation on a vector space, and I'm saying that the collection of I can tensor. There's an operation of vector bundles on the dual vector space, or sheaves on the dual vector space on the category of differential equations on this vector space. Right. So in particular, for example, why is that a spectral decomposition? Take, if I give you an open subset of the dual space, I can take the module, which is the structure sheaf of that open subset, and I can tensor with that. So that's an analog of restricting to that open subset in momentum space. So it's saying, and it really tells me that the category of differential equations under my vector space sheafifies over this dual vector space. There's a set for every open subset. So this is microlocalization. For every open subset in momentum space, there's a notion of system of differential equations that live in that over that open subset in momentum space. So that's what we're doing. It's not supposed to be deep in that, right? Yeah. Yeah.
Where does this last equivalence come from?
Let me give you a map, and to give you at least a map, if I have a functor. Let me just say, so if I have a module category, that means I have a functor from R mod to endofunctors of C. If I have this given this guy, that gives me that means I have an action in the morphisms. So I take the unit in here. So I have the unit in here, which is R itself. It has to go to the unit in here, which is identity endomorphism C. And so the endomorphisms in R mod of R, which is R, gets mapped to endomorphisms in C of the identity. So that's one direction at least. Yeah. But on the other hand, this category, R mod category is generated by its unit. Every R module is given by a bunch of copies of R with a bunch of maps between them. Once I understand the action of the unit and its endomorphisms, I understand the action of the whole category. So that's what it means to be linear over a, and there's a version of this linear. So that's what it means to have a category that's linear over a scheme. There's a similar version for a stack or over any. I mean, I was giving you an affine scheme. You can juice this up. So that's a notion of a category living over a space. Now I don't want just a category. I want a monoidal category. So in my story, I'm interested in this not just as a plain vanilla category. I'm interested in it with convolution. And so I need a stronger statement. There has to be an interaction between this structure and the convolution structure. And let me say I want to get to something more concrete in a second, but let me just say what's the good of giving such a structure? If I gave you such a structure in our setting, then we would be able to talk about. So let's suppose we had the kind of dream I proposed, the kind of Harishchandra Fourier transform dream, and we'll modify it, and we'll get something close to that. But the initial idea was, suppose I have something like Z mod. Suppose I had a functor from Z mod, which is, if you like, quasi-coherent sheaves on this space C. Suppose I had a functor from this to the center, an isomorphism between this and the center, even if it wasn't isomorphism, but with D of G mod G. If you had such a structure, which is the center of the group algebra, that would tell you the entire representation theory of G, which live over this space C. In particular, this would give, if I give you a point lambda in C, it makes sense to tensor. You could look at differential equations, G mod G, with infinitesimal character lambda. It's just going to be the fiber. It's just a D of G mod G, tensor over Z mod with kind of evaluation at lambda. So if you have such a statement, it makes sense to talk about these categories of differential equations whose infinitesimal character is strictly lambda. That's one of the things it would give you. Another thing to give you, let me point out, if you don't care, you say, OK, G mod G is nice, but what about G mod K or G mod K mod H? I would get the same thing. Because this is a center, because this guy has a structure of a center, it follows automatically that I'd get the same structure for differential equations on G mod K for all subgroups K, or if you'd like, I could get intertwiners, G mod K mod H for any two subgroups H. You get a tensor functor from the same guy into all of these. So all of these categories would all live over the same space. You can decompose over the same space. Okay? That's just abstract algebra from the fact that this is a center. Okay? So that's the relevance to some of the things we're talking about, that all of these categories we're interested in all automatically decompose. Now, this doesn't exist. I'll give you some small modification that does. So that my point is a theorem, not a fairy tale. But that's the kind of, you take the entire kind of geometric representation theory of G would live over this space. That's this kind of microlocal decomposition. OK. So that's the. Now let me point out, this is the basic problem. Is why this can't, in this way, it can't possibly work. Because, as we were saying to Giannis, if I look at this Harishchandra system, here's a very naive question you can ask. Take this Harishchandra system. This was given by differential equations on the group, and you mod it out by this, center acts by this character. And then you ask this stupid sounding question: how does the center act on m lambda? Right? I've imposed the equation that the center acts by lambda, and then you ask, how does the center act? And the answer is not by lambda. The answer is by lambda plus a whole collection of translates. And the basic point is this is a one-sided ideal. It's not a two-sided ideal. That this Z is not in the center of the ring of differential operators. This ring doesn't have any center, but scalars. So imposing an equation on the center on one side doesn't tell you how the center acts on that module. So it's not true that the center acts on m lambda by lambda. So my basic dream fails before I even started. So now I wanted to work out in detail the case of C star. And give you the kind of answer you do have, the kind of answer. So I'll give you an answer in the case of C star. Again, for C star, you don't need any of this nonsense. But the kind of answer, the way I want to give the answer is going to be one that will generalize to arbitrary G. OK. But I think C star also illustrates this problem well. So OK, so here's our example. Take the group to be C star. Before we did the Fourier transform on C, now we'll do the Fourier transform on C star, which actually is a reductive group. So here our center is polynomials in ZDDZ now. Yes?
You're about to give an example why this.
Yeah, I'm about to. Yeah, so I'll give you the example where G is GM. Yeah. So let's write down what all these guys are. So we have the group is C star, and I'm looking at the center of the enveloping algebra, which is just polynomials in one generator. This is the vector field ZDDZ. And so my Harish-Chandra system is just the differential equation ZDDZ f equals lambda f, just the eigensystem for ZDDZ. And I don't know, it makes me more comfortable thinking about it in terms of flat connections. This is the same as saying that f is the solution of the flat connection, d minus lambda dz over z, f equals 0. So we're studying the local system with d minus lambda dz over z, or the eigensystem of this equation. So whichever makes you happier. And then the basic problem is that, well, again, if you think about this as a local system, the natural invariant of a local system is the monodromy. So we have a monodromy of this differential. So this local system up to gauge equivalence is given by the monodromy, which is e to the 2 pi I lambda. That's the fundamental invariant of this up to isomorphism. Or you could say it on this side, just that m lambda as a system of equations is isomorphic to m lambda plus n for any n integer. I just take the function f and multiply it by z to the n. Right? If f solves this equation, then z to the nf will solve the equation where I shift lambda. Okay. So the same system of equations, so the systems are all isomorphic for all integer translates. So if you ask how does the center act on this module, well, z acts by lambda plus z. The eigenvalues of this operator as a z-torsor. It's all the translates of lambda up here, okay. which is fine. So really the only invariant is the monodromy. So in other words, we can't hope to do this spectral decomposition over the lambda line. The best you can hope for is the lambda line up to translations. Yeah, just by functions. So I'm just saying that z d by dz and z to the n don't commute. I'll get the sign wrong, but plus did I? Presumably the sign is wrong, but it's something like that, right? The operators z d by dz that picks out homogeneity. And multiplying by z to the n changes the homogeneity of a function by n.
I think when you define m lambda, you mean the module generated by the solutions of this.
Well, yeah, I was writing it poetically as the system of equations. So m lambda, sorry, maybe I shouldn't be poetic. M lambda is the ring of differential operators in C star modulo the ideal, modulo the ideal generated by, z d by dz minus lambda. So I think of this as the system of differential equations. I'm not going to look at solutions. I'm just looking at the system of equations. So, okay.
Is this supposed to be analogous to the failure of the categorical? Because here it seems to me the issue is the center. This center is the center of UG.
Yeah.
But in the categorical version, you really did define the center to be the center of DG.
That's right.
So it doesn't seem very analogous.
That's right. I mean, absolutely. But if I ask you what is the natural space of parameters for differential equations on G mod G, I think the natural guess is this spec of Z. The natural systems you have these Harish-Chandra system. If I give you a system of equation, you might ask what lambda does it assign to? Or if you're thinking microlocally, which kind of fiber of the moment map does it live on? That question doesn't make sense directly, microlocally, but we're trying to make some substitute for that, for a system of equations. And so you're right, there's no reason a priori that it would have to be exactly that, but that's a natural family of equations that I have. That's a natural commutative ring I see there. And the answer will be something very close, does work. So it is somehow the right kind of answer. Okay, so in other words, we can hope. Does this make sense? So that tells you that you can hope at best to spectrally decompose this category of D of C star modules over C mod Z, C up to translation, or analytically I would say C star, but I want to say everything algebraically.
Let me just tell
Yeah.
you, because this equation there looks like the center F by lambda. So what you mean is that if I want to think of the module as functions, I should think of all the multiples of F by integral powers of Z, right? So if I want to think of,
Yeah.
I have one solution F, and then I take Z to the n
Yeah.
times F, and that's my
Yes.
Z module.
Yeah, that's right. OK, so and you can do so. So in other words, what does it mean? So decompose over C mod Z, i.e., I can tensor not with vector bundles on C, but with I should be able to tensor bundle with vector bundles on C mod Z. In other words, i.e., Z equivariant vector bundles, Z equivariant vector bundles on C. So that should be my natural tensor category that's act is Z equivariant vector bundles on C. But let's say that a little better. So what does it mean? Where does this Z mean? That means that rather than looking at the ring, I need to replace the ring that I was looking at. So I replace Z, replace just the ring Z, which in my case was polynomials in lambda, by polynomials in lambda, where I adjoin the operations of translation. This is the action of Z. So these are the operators that translate lambda by 1 and minus 1. OK. This is the groupoid algebra for the action for Z acting on C. So that means I have to build in intertwiners between lambda and lambda plus 1 and lambda minus 1. Yeah. So I'm adding an operator, which I'm just adding. I'm having a ring where I add to lambda, and I'm adding a new variable where the commutation relation is sigma. When I commute sigma past lambda, it translates lambda. Lambda goes to lambda plus 1. So it's a ring of difference operators on the line. I take the functions on the line, and I adjoin a difference operator, which shifts lambda by 1, and its inverse. So this is just the groupoid algebra. I have the group Z acting on C. So I look at functions on C, and I adjoin to it the group algebra of Z. So this part is just the group algebra of Z. So I'd like to talk about groupoid algebras, but maybe before I talk about groupoid algebras, let's just point out that that this has now become silly by the Fourier transform, the multiplicative Fourier transform, or the Mellon transform. So the Mellon transform in the algebraic, the kind of algebraic analog of the Mellon transform here is just that the ring of differential operators on C star, just like we had in the additive case. So that was the ring where I take functions in Z and Z inverse, and I adjoin the operator Z d by dz. This ring itself is just isomorphic to the ring of polynomials in lambda adjoined sigma inverse. These two rings are just isomorphic under the map where I replace Z by sigma and this by lambda. So if you like, this is the ring of difference operators. So this is difference operators, if you like, on C. And these two rings are just isomorphic. And this is kind of an algebraic version of the Mellon transform. It's saying the Fourier transform of multiplication by Z on C star, it becomes translation in momentum space. Okay, it's just the multiplicative version. So I certainly have an action of this ring everywhere. It's just a different way of looking at my original ring of differential operators. Now maybe, so what I'd like to do, maybe, I don't know if it's, so I'd like to write this in a very confusing, complicated way. Maybe I already did. But I'd like to do even more. Yeah.
Sorry.
Yeah.
So a spectral decomposition was
That's right.
to the center of your category.
That's right. Yeah, so I'd like to give, so now I'm changing my model from modules for ring to modules for, yeah, so, okay, so.
So now you want modules for this
yeah.
to the center.
That's right. So I'm going to replace, so I want to map from some symmetric monoidal category, some monoidal category to the center of some guy.
Yes.
Now, before, my source of symmetric monoidal category was just R mod for some commutative ring R. That's a nice source.
Yes.
So sheaves on an affine scheme. Now I want to replace them by sheaves on a stack. So suppose I have, so now I'm going to replace R mod by modules for, I'll replace them by something like R mod equivariant for G. So here I'll have a G will be a groupoid. Acting, so in other words, if you'd like, this is going to be sheaves on spec R mod some stack. So that's going to be another tensor category that I'm going to replace.
Yes.
So here I'm going to replace C. Before this was modules for C. Now I'll replace them by C mod Z. But rather than think of C mod Z directly as a stack, I'm going to present it as a groupoid algebra. So if I have a groupoid scheme, so I have a scheme X, and I have does everyone, should I explain what a groupoid scheme means? Or yes?
In which category are we now? What is C mod Z?
C mod Z is a stack. It's C complex algebraic geometry. I don't know. It's not an algebraic stack, but it's a stack.
Where does this algebra C lambda sigma sigma inverse come into?
Right. So C lambda sigma sigma inverse, I claim, is going to be a groupoid algebra. So given a groupoid, just like I have a group algebra, so I have a group algebra, its modules are representation of the group. Given a groupoid algebra, its modules are equivariant sheaves for the groupoid. So my source for tensor categories is going to be I'm going to have a space.
Modules for this thing.
That's right. So maybe I should.
But then how did it go to the center?
Oh, I haven't. You mean in this case, where is it going to the center?
Yes.
Right. OK. So I kind of pulled a little. Tried to pull a little fast one there, because really the category. I'm supposed to be looking at the analog of G mod G. In my case, G is C star. So the category I'm supposed to be mapping to is D of C star mod C star. And I was ignoring the denominator. I was ignoring. So inside of here, there's already a symmetric monoidal piece, which is just D of C star. Because the group is abelian, I can't do this in the non-abelian case. In the abelian case, I can decouple the numerator and the denominator, saying that inside of sheaves on C star mod C star, I can just think of D modules on C star. And this is a symmetric monoidal category living in the center. So this is, and I was just saying this.
So how does the center of D C star mod C star? No, that is the center.
That is the center. This is the center of D of C star with convolution. Now, D of C star with convolution happens to be symmetric monoidal. So this is the thing. Even if you start with something commutative and you take its center, you get something only braided. This guy's only braided.
So in this particular case, the thing factors through this.
That's right. And in fact, it just is. So the point is that this is vector bundles on C mod Z, or vector bundles on C that are Z equivariant, or the way I got it was as modules for this, which is functions on polynomials in lambda adjoined Z, the groupoid algebra of the Z action on functions on C, modules. Okay. Does that make sense? So there is a commutative. So again, this is saying something very complicated that everyone already knows. It's just the shift invariance of these eigensystems. But you can say that shift invariance is saying that this system of differential equations in C star is linear over not polynomials in lambda, which is what we initially guessed. Initially, we guessed that you can fix lambda be a number. It's not linear over polynomials in lambda. It's linear in polynomials in lambda once you add shift. Okay? And that's because that literally is kind of half of the category you're looking at. It's the numerator half. Maybe, I don't know, people's patience is probably running out. I'm going to give a statement that's exactly like this for a non-abelian group. So maybe I should write it down before I say more. For a non-abelian group, there's going to be a completely analogous statement. If I look at differential equations on G mod G with convolution, I'm going to give you, this is, I should mention collaborator, give you a tensor functor from a category which is going to be quasi-coherent sheaves on the same parameter space, roughly, but equivariant for some groupoid. Or let's say less poetically. Instead of looking at Cartan mod the Weyl group, which is what C was, I'm looking at the Cartan mod the affine Weyl group. So the affine Weyl group, this is the analog of C mod Z in the abelian case. So this is going to be what the theorem is. So it tells you that the category spectral, as opposed to C, which was Cartan mod the Weyl group. So so we were wrong just by a lattice. So there is a spectral decomposition of this system of differential equations. There's kind of you can work microlocally, not locally in this space, which you might have thought, locally in this space up to translations, which is this space. Okay. So that's the theorem, and there's a lot of things I would like to say, but I'm not sure which ones are the most interesting. So let me just sort of give some bullet points of things that I could talk more about. But one thing to say is you could ask when you take the classical limit, when you take symbols, go from differential operators to cotangent bundles, where is this extra lattice coming from? Where does it go? Well, and you can see that very nicely in the abelian case where it comes from, and in the non-abelian case it becomes exactly in Go's actions of regular centralizers and all centralizers. So the extra translation symmetry, the part you were missing, its classical limit is this in Go action. So that's one story. The other story I could say is really what this groupoid is. There's a very nice presentation of this groupoid in the Langland-Zuhl formulation, which is how we actually prove the theorem. And that I can explain concretely in the abelian case, and I think that's kind of fun. Just write the same groupoid in terms of loop Grassmannian for the dual group, just for the torus.
Can
Yeah.
you explain
Yeah.
a little bit what you said about the classical limit?
Yeah. So let me just say it in the abelian case first. In this abelian case, so we realized that we needed this translation. You ask, where did this translation come from? In the classical limit, they came from something obvious that you just didn't think you needed, right? So if you look at, so here again, we have the differential operators on C star. We're identifying with polynomials in lambda adjoined with this translation. This is the Mellin transform. Now what happens when you take symbols? When you take the classical limit, this becomes functions on the cotangent bundle of C star. So I want to think of cotangent bundle of C star as C cross C star with a projection down to C. Right? So this is my lambda line. Right? It's a cotangent direction. Right? So that's my analog of the adjoint quotient. So what happens here? Well, in the classical limit, these guys just commute. It's C of lambda and another operator, sigma and sigma inverse, where sigma and sigma inverse are just coordinates, are the coordinates on the fiber C stars. So we have here we have a space which is, I don't know how to picture T star of C star. Right? So we were focusing on lambda, which is a coordinate on the base. You also have the fiber coordinates, which are functions on C star. And as you know, if you like Cartier duality, functions on C star is isomorphic to the group algebra of Z. Right? So functions on C star, that's polynomials in Z and Z inverse, is isomorphic to the group algebra of Z. That's where this Z is coming from. What's happening is that in the classical version, the functions on the fiber and the functions on the base commute. So we just decoupled them. We only looked at the polynomials in lambda acting. When you quantize, the functions on the fiber and the functions on the base no longer commute. And what that means is that these functions on the fiber end up moving lambda. when you conjugate them through a lambda, they translate lambda by an integer. Right? So what you realize is to quantize it, you can't just try to quantize lambda. You have to quantize this whole integrable system. Does that picture make sense before I say the non-abelian version? So what's the non-abelian version? That's this thing that I don't know. I guess we haven't gotten to in the seminar yet, but this invariant collective motion. So the classical limit of this construction is if you look at T star of G mod G. Remember, this is just commuting elements of a group element and a Lie algebra element. Right? So this is just commuting pairs. And this had a map, which is this characteristic polynomial map. So let's call this I for inertia. This is, again, commuting pairs of X in the Lie algebra. Let me choose an invariant form. And G in the group that commuting up to conjugation. Which is just take the invariant polynomials, characteristic polynomial of X. So take my invariant functions, apply them to the Lie algebra element. So this is, think of this as G dual mod G. That's the value of invariant polynomials. Before we were trying to just quantize these guys. So functions on here quantized to be the Harishchandra center of UG. This guy quantized to be my D of G mod G. But what I need to do is there's a family of groups which is called J, which is the analog of the picture I had before. So I think I drew a picture of J in my previous talk. J it's an abelian group scheme. Commutative group. It's not abelian group. So it's a commutative flat group scheme over C, where the fiber over lambda is so J sub lambda is kind of the regular centralizer of lambda. It means a centralizer of a regular element with characteristic polynomial lambda. So generically, it's just a maximal torus. If you have a regular semi-simple element, then this just looks like the maximal torus. H. So the generic fiber looks like a maximal torus. But the special fiber, when say lambda is nilpotent, this becomes something centralizer of a regular nilpotent element. This is very close to what we were doing in the morning seminars. We saw generically we have an action of these tori on some generic locus in some cotangent bundle. The point of Ngos's construction, in the proof of fundamental lemma, use the fact that this entire family of groups acts on this family of groups. Well, actually, let me just say there's a homomorphism. Okay, I don't know which way to say it. Anyway, there's this family of group acts on the fibers of this map. So that's the missing directions. In order to and J itself is what does this J look like? It looks it's symplectic. It looks roughly like the cotangent bundle. Infinitesimally, it looks like the cotangent bundle of the base. Okay. So it's some group version somehow. It's the Lie algebra of this J is the cotangent bundle of the base. So it's a kind of exponentiated version of the Lie algebra of the base. So you're missing kind of half the directions. So Ngo gave an action of this family on here.
Can you describe that action?
So can I describe that action? Yeah. So there's Ngo's construction is a cheap one where he says over the regular locus. So up in G. Sorry. Let me. Yes. Okay. So over G dual, there's two. He's going to give a map of group schemes over G dual. So I'm going to pull everything back to G dual. So over G dual, one group scheme is again it's called the inertia, where the fiber, which is the fibers are just the I sub x is the centralizer in G of x. Just the family of centralizers. So that's a very non-flat group scheme over the Lie algebra.
Yes.
Then there's another flat group scheme, which is chi pullback of J. So J lived over the base of the characteristic polynomial map, of the adjoint quotient map. This is where J lives. And you can pull it back to G dual. So that's a family of, that's a flat abelian, flat commutative group scheme over G dual. And Ngo pointed out that there exists a unique homomorphism. And that homomorphism is completely determined by the fact that on the regular locus, inside of here you have G dual reg, where these two are just equal. And the complement has codimension 3. So we just used Hartog's. That's what I mean by the cheap construction. For GLN, you can give a simple explicit description. Somehow the point of our construction was to we give a new construction of this using geometric Satake, which is what.
Can you remind us why it was so useful to you?
Can I remind you why it's so useful to him? Yeah, maybe just in. Yeah. So let me just point out the basic.
That's sort of just an abstract.
Yeah.
Just a removable singularity.
That's right. But yeah, so the point is that the thing that you're putting at the singularities is something interesting. In particular, for him, all the important was a connected components group. So if you look at J sub 0, say, so let's look at SL2. You take 0 inside of C. Yeah. So if you look at the zero point in C, the fiber is C cross Z mod 2, the centralizer of the centralizer in SL2 of a regular nilpotent matrix. While I sub 0, of course, is just the entire group SL2. So it's important for him that you have for him the only thing that's important is these component groups. So what Ngo was looking at in particular, he was looking at he had some curve over a finite field. You could do it over C. You have a curve, a map to, you have a Higgs bundle, which is a map to G dual mod G. You have a principal G bundle, a section of the adjoint, maybe twisted by some line bundle, doesn't matter. So you look at the collection of all such maps. This is what's called this moduli space of Higgs bundles, G of C. So this maps to map from C to the adjoint quotient base. This is the Hitchin map. And Ngo was interested in, so Ngo realized that the fundamental lemma is a statement about the cohomology of, you can describe endoscopic decomposition in terms of action, in terms of the cohomology of fibers of this map. And what Ngo pointed out is that this action, another way to write this action is that there's a group scheme, group stack, the classifying stack of J. So we're off by a classifying space, but let me just call it maybe C mod J. This C mod J acts on G dual on this stack. That's a reformulation of what I have. So just reformulate what I write is that this classifying stack of J acts on here. What that corresponds to is saying that if you look at the fibers of this Hitchin map, they carry there's a flat family of commutative groups over the base that acts on the fibers, and whose component groups you can describe explicitly, and that is gives the endoscopic decomposition of the fibers. You have some finite abelian groups. So what he got at the end out of all of this was actions of some finite abelian groups on cohomology of Hitchin fibers. But it all comes directly out of this map. OK, so yeah. So what we're doing is, well, we give a different construction of Ngo's map, which might be not so interesting from Ngo's point of view, except that it enables it to be quantized. So what we're interested not in this question about cotangent bundles. We're interested in the question about differential operators. So we want an analogous construction for differential operators. That's what this functor is. And we're interested in order to be able to give spectral decomposition for systems of differential equations on G and related problems. And so let me just tell you where this groupoid, where it comes from. It's OK to. So I want to give let me give you something very simple, stupid way of saying this C star example, but that will generalize. So let me again, just like we did in the abelian case, let's replace C star by some torus. You know, just I don't know, just so I don't, so we keep track of the torus and the dual torus. Okay. You could take T to be you could take L to be 1, but I'll just call it T. So I want to describe functions on this torus. That's my polynomial ring in several variables. Well, you know, Cartier dually, that's the group algebra of a lattice, right? So lattice lambda is the lattice of characters. It's Hom from T to C star. Or I could think of them as co-characters, Hom from C star to the dual torus. Okay? So I'm going to use this kind of Cartier duality, and I want to realize that the following way. The same space lambda, okay. So the space lambda, so now let's give a complicated description of lambda. Lambda can be written as a set of cosets of T check. So I take a local field K, and I look at cosets T check of K over T check of O. I'm taking K to be, say, Laurent series in some variable T. So look at Laurent series, invertible Laurent series over invertible Taylor series. That's a complicated way to say the integers. Now here, there's some non-reduced structure, but I'm going to ignore it. That's not going to affect my story. So let me think of lambda as being this coset. Okay. So what am I trying to do? I'm trying to recreate this ring. I'm trying to recreate this picture. So the function was fiber was functions on C star. Now I want the base, which is functions on C. Where does that functions on C come from? So here, on the other hand, functions on so that base here was little t dual. Sorry, everyone see what I'm trying to do? I'm trying to take cotangent bundle of T mapping to little t dual, and the fiber looks like T. So I've described functions on T, Langland's dually, if you'd like. Now, what does functions on the base look like? Well, functions on T dual, that's the equivariant cohomology ring of a point. Or if you'd like, the cohomology of the classifying space of the dual torus. Okay. So that's the same ring. So this is the coefficient ring for equivariant cohomology. Now I'm ignoring grading. This has some even grading. I'm thinking of this as ungraded. But let's just ignore that. Okay. So this ring appears as the natural coefficient ring in equivariant cohomology. So if you put these two things together, you get the following picture so let's look at the equivariant cohomology ring of this Grassmannian, equivariant homology of the Grassmannian. So this is, I guess I should give this a name. This is the affine Grassmannian. So I'm thinking of lambda as the affine Grassmannian. Check. So if you look at the equivariant homology ring, or maybe in more Hecke-ish notation, I'm looking at homology of the double cosets construction. T check of O. Okay. So let's look at this Hecke stack, if you'd like. Double cosets of T check of K by T check of O. And I'm going to look at its homology. And this exactly combines my two. This is exactly isomorphic to functions on T star of T. It exactly combines the two pieces I had before. I had the equivariant parameter, and I had the lattice. Okay. So that's a very complicated way to say function on T star of C star. I hope you agree. Okay. But now the point is that now I've written this. This now looks like a Hecke algebra. Right? When you see homology, I want you to think like distributions. So I'm looking at something that measures on a double coset space. So measures on a double coset space have a associative algebra structure. In this case, it happens to be commutative. And so this is my Hecke algebra, and that's my commutative ring of functions on this space. Yeah. Yeah.
Why have you taken the things commutative? Why have you taken the quotients twice?
That's right. Well, the two quotients are equal, so because it looks nicer. I mean, right? Because this is the same as the affine Grassmannian times point mod T check of O.
So the second means something.
Right. If I'm taking equivariant homology, or if I'm taking equivariant homology of the space, or if I'm looking at equivariant derived categories, I feel that extra stackiness, right? So this is a stacky version of the Grassmannian. On the level of functions, of course, I don't feel that difference.
And where did this isomorphism with T star?
Well, if you like, I'm really just, you could just see it just by cheating. I mean, this space is a product. And I'm just getting the homology of the Grassmannian. The Grassmannian is just the integers, or should I just lambda. This just is the set lambda. So I'm looking at measures on lambda. That's the group algebra of lambda,
Yes.
which is functions on the dual torus. And the equivariant cohomology of a point is polynomials on the Lie algebra dual. So I'm not, yeah. So that's isomorphism. So this ring that I was interested in. Now, so far, let me notice that I've explained to you this guy is a ring. It's a Hecke algebra. It has this double coset structure. That gives the ring structure. Now, but I was interested in that this space T star of T is not just a variety. It's a family of groups. Right? T star of T mapping to T dual is a family of groups. That means that this ring should actually be a Hopf algebra. There's a co-multiplication here. I need to see the group structure somewhere. And algebraically, you see that this guy has not just a multiplication, but a co-multiplication. Where is that co-multiplication coming from? Well, whenever I have homology of any space whatsoever, I always have the cup product. I mean, so cup product I think of as a product on cohomology or a co-product on homology. So this is the kind of paradigm I want to make, because I want to take. So I don't know what language is. So whenever I have kind of a Hecke type algebra, I can think of it as kind of a groupoid. This is the same as a groupoid. It's point mod k cross point mod k over point mod g. Or if you'd like, whenever I can imagine whenever I have a space x mapping to a space y, I can look at a groupoid, which is x cross x over y. Or if you'd like, whenever I have a groupoid acting on a space x, and then I can let the y be the quotient, x mod g. So let's look at any of these kind of situations. They're all kind of the same situation, depending on your choice of letters. So if I take measures on the groupoid, my version of measures is homology. If I take homology of such a groupoid, it's always going to be, so it'll have two structures. One is a Hecke kind of algebra. It'll have an associative multiplication, and it'll have, so let me just write this. So if I take homology of one of these beasts, G means any of the guys on the top row, right? It's associative algebra from convolution, but it's also a co-commutative co-algebra from cup product, if you like. And if you don't like the topological version, I'm just saying that measures on a space is dual to functions, and functions have a ring structure. So measures have a co-algebra structure. So I'm saying Hecke algebras are naturally Hopf algebroids. They have a multiplication, they have a co-multiplication with a natural compatibility between them. And because of this, if you look at modules for your Hecke algebra, this is always going to be symmetric monoidal. When I say modules, I'm using the algebra structure, but the tensor product is coming from the co-algebra structure. Okay. So that's my construction here. So here I've written, in a very complicated way, functions on T star T. I've written it as a homology of this groupoid. This is some kind of groupoid. And that's a way of explaining the structure. Now, why would I go to all that pain is that now it's very easy to quantize. In this picture, in this Langlands-Zuhl picture, it's very easy to quantize the space. All I have to do is add one more parameter to the group. So this then.
But in the language of these
Yeah.
diagrams that we have there,
Yeah.
are you really referring to G or to Y in the left?
This is different.
On the left you have a.
I'm saying. Yeah, X mod the quotient stack Y.
Quotient X.
That's the analog in the Hecke situation of point mod G.
So this G here is the quotient on the lower board.
Yeah. G is the groupoid. I'm saying the homology of the groupoid. And you know, this homology of the groupoid is something very natural. This just means, if you think what a groupoid algebra is, it just means sheaves on X that are equivariant for G. Or it's trying to be, if you're in a situation where descent hold, it's trying to be sheaves on the quotient stack.
Right.
That's why it's commutative.
Okay. So
It's trying to be sheaves on Y.
okay.
So that's why these guys are always commutative. So in my situation, though, well, here in this situation, I can replace this. So now I want to quantize. And the quantize becomes something really silly. You just you take the exact same story, the same Hecke algebra, but now you add equivariance you add one more equivariance, which is equivariance for GM action. So there's an action of a group which is rotating the loop, so GM is acting here on C Laurent series T. It's acting on the punctured disk, so just rotations of the punctured disk. Okay. So we're going to work a version where we work equivalently for rotations of the punctured disk. So I don't know of arithmetic analog of this. I guess the closest in this paper of Zhu and Xiao, they have a version of Satake equivariant for Frobenius map. It's not really exactly analogous, but anyway, it's a version of, we're using a version of the loop Grassmanni equivariant for an extra symmetry, which is the symmetry of this punctured disk. And this algebra, again, you can, all this abstract stuff about it works the same. It's still a Hecke algebra. It still has a symmetric monoidal category of sheaves. But this algebra ends up just being now the ring of differential operators on C star. So this quantization is just achieved by adding a parameter. Really, I have the Riesz algebra for that, where H bar is the parameter in the cohomology of GM equivariant cohomology of a point is polynomials in one generator H bar. So that's where the parameter comes in. OK, so let me just so maybe let me finish by saying that we're on the other side. It's a Langland's dual statement. So sorry. Thank you. T. Yeah, sorry. So I'm saying that differential operators on the group T have a Langland's dual description as equivariant homology of the loop Grassmannian, where this where this presentation as a groupoid algebra, where you see the
And you've suppressed the T.
No. And the point is that you've written it as a groupoid algebra. You've written differential operators on T in a groupoid algebra. This presentation directly gives you the presentation as polynomials.
What is this D lower H bar T?
Yeah, so I need to give you, so if I look at equivariant homology of a space, it's a module over a ring, which is equivariant homology of a point. There's the coefficient ring there, which is polynomials in one variable. So because if I remove the equivariance, I'm supposed to get back there. So I have a family over the H bar line, which is, I take the ring of differential operators on T, that's a filtered ring, and I take its Riesz construction. So I just take if I have a filtered ring, I can think of it as a flat ring over A1, which is equivariant for GM. So instead of, so where at 0 you get the associated graded. So you can always interpolate between a filtered object and the associated graded. So I'm saying that, so think of the family, so I think of differential operators as appearing as a value at 1, as a fiber at 1 of a family, where at 0 I get the associated graded, which is the function from the cotangent bundle. So that's the way, and the way this family is naturally appearing in geometric representation theory, this kind of very common theme in representation theory is that these these quantizations come from adding a equivariance on the dual side, add to just equivariance for GM. Whenever I add equivariance for GM, that gives me a one-parameter deformation of the object I was studying.
Sorry, but I'm
Oh, of this ring? Sorry. Yeah, it's just that the Riesz construction means I'm taking the direct sum of h bar to the I d less than equal to I. You take your, so that's a, so I'm taking, so this is a module, this is a C of h bar algebra, which is the direct sum of the filtered piece of degree at most I of d with coefficient, which is h bar to the I. So if I set h bar to 0, this exactly gives me the associated graded. So the action of h bar.
In previous notation, this would be d sub t, right? So
Oh yeah, yeah. Sorry. Yeah. Okay. It's a ring of differential operators, but now with a Riesz parameter.
Why are you setting h equal?
Because the action of h moves you from one piece to the next. So the multiplication by h bar moves you from the. So if I set h bar to 0, I'm quotienting it by the action of h bar, and so it's exactly quotienting the inclusion of d less than equal I by d less than equal I minus 1. Yeah, so maybe I should just state the theorem. So again, so the theorem it's up here, but let me say where this appears. So what's really going on here? Where did this come from? So this was the theorem. It was a construction of a map with various nice properties. But in particular, it's a tensor functor from a symmetric monoidal category, which is functions on this space to here. And the place that this algebra is appearing, so this has various concrete descriptions. This is modules for something I'll call WIT, or WH secretly for Whitacre. But this guy, so it's modules for, and so this is an analog of a groupoid algebra. So this is an algebra. This is what's called a bialgebroid, but what is this guy? It's concretely, it's the homology. It's the same thing. It's the homology of the affine Grassmannian for the dual group. So it's kind of the spherical Hecke algebra with a GM. So this is where so there's an actual groupoid algebra. So this is some funny groupoid. And I'm looking at its groupoid algebra. And it modules for this groupoid algebra some symmetric monoidal category and can be identified with this particular guy. But this is really how it appears. And the proof uses geometric Satake. So the proof is based on the fact that representations of G are identified with sheaves on this same double quotient space. Maybe I don't have time to give the proof. The construction of this functor, it's become something very naive on the other side of Satake. So that's where this guy is coming from, where this groupoid is coming from. Yeah. Yeah. Right. Well, yes, I'm going to talk again on Thursday, and not expecting anyone to go to too much of this, but where I'll try to explain why this is a Whitacre thing. So this ends up having a natural identification with this same algebra has many descriptions, and one of its other descriptions is the same guy can also be given by differential operators, kind of by Whitacre differential operators on the group. So I look at differential operators on the group G, and I look at ones that are kind of n psi bi-invariant. Or if you like, this is trying to be differential operators on the would-be space G mod n psi. So here psi is a non-degenerate character of the group of upper triangular matrices. Right. So this guy is the Whitacre kind of reduction of differential operators in the group. And this realization is compatible with this is the yeah.
Any reason why I would have
Yeah, so that,
these two things be?
so that, then, if it could be very vague for a second, the basic reason is Whitacre normalization. Is somehow the statement, so in geometric Lagrange, the way that Whitacre normalization works is that on one side, taking Whitacre vectors corresponds on the other side to taking global cohomology. So that's somehow that's a version of the Whitacre normalization in the geometric Lagrange setting. So in the geometric Satake formalism, so there's a version of geometric Satake, I should write their names because the version I'm using, there's this derived geometric Satake of Bezrukovnikov and Finkelberg, and they identify the category of sheaves on this Grassmannian with or without the GM. But the equivariant, it's important here that it's the equivariant derived category. They identify this derived category with sheaves on, well, with UG modules, with Harishchandra bimodules. Anyway, they give it explicit equivalence of categories between sheaves on the Grassmannian with equivariant and G equivariant UG modules. So these are, if you'd like, these are the same as GK modules for the kind of the group case of GK modules. They're modules for G plus G, integrable for diagonal G. So, and here again, there's an H bar. When H bar is 0, you get just a G dual mod G. So the familiar geometric Satake, the representations of the group G are appearing here just in the denominator. The derived version contributes this numerator. This numerator is something you don't see in the classical Satake or usual geometric Satake. This numerator comes from the equivariant, from saying by everything being equivariant cohomology, from the derived aspect. So that introduces this denominator, this numerator, and their equivalent. One of the features of their theorem is a Whitacre normalization. That on this side you can perform taking Whitacre vectors. You can take, given a UG module, you could take its Whitacre vectors. On this side, you could take just hypercohomology, and these commute. So that's kind of a just normalization of their theorem. When you spell out what that means, it ends up giving. So we kind of leverage that statement to giving the equivalent, that category. So yeah, we use some say that this category of modules for this bi-Whitacre differential operators, or this bi-Whitacre D modules, using their theorem, we identify it with modules. Well, modules for this particular homology. So this funny homology thingy, modules for it, using their theorem, you can identify with Whitacre modules for D. So that shows that, so it's something cool here is that a priori a Hecke algebra needn't be symmetric monoidal, Hecke category. So this one is really symmetric monoidal in the strict sense. So somehow it's even better than the Satake category. The spherical category is not actually as commutative as the Whitacre one. So this guy is somehow strictly symmetric monoidal category.
Why is that?
I'm sorry?
Why?
Well, I don't know, because it's comodules for strictly co-commutative coalgebra. It's because the cup product is really commutative. The multiplication here comes from cup product. So it's another realization of this kind of multiplicity one, that Whitacre Hecke algebras are commutative. Here it's coming from the fact that cup product is strictly commutative. And then the point is that this theorem is taking place really on this dual sided. No, not for h equals 0. For h equals 0, you get G dual mod G. But then I'm just saying that inside of here, there's a G dual direction, which is all coming from the derived stuff, and then there's point mod G, which is where the usual geometric Satake. Usual geometric Satake is about just representation. I have my G and G duals backwards from how we would really like it. But that's how it comes up here. OK. I have to go pick up my son, so I have to run. Thanks.